So let me share my screen. Hope you can see my screen. Okay, we've covered until type 4. Wherein the integral is composed of a combination of tangent and secant, and another one is the cotangent and the cosecant. So we have two cases under type 4. One case is when the exponent of the tangent or the cotangent is an odd positive integer, and the exponent of the secant and the cosecant is any real number. Now for case 2, it's the other way around. This time, m is any real number, and that's the exponent of the tangent or the cotangent. But this time, the secant or the cosecant is having an even positive exponent. Okay, so those are the things that we have covered, the last topic that we have covered last meeting. So for this afternoon, we will continue with the last two. Actually, the last type is the easiest of the 6. And the type 5 is only comprising one function. So it's either an integral of a secant and a cosecant. And our limiting condition here, the limiting condition is that the exponent of the secant and cosecant should be even and positive. So you could see here even and positive. So since the secant or the cosecant in this case is positive and even, then we'll be using a identity that we have already encountered in, if I'm not mistaken, types 4 and 5. Okay, so the identity that connects the secant squared to the tangent squared, the one that you are seeing here. And the other one is the identity that connects the cosecant squared of x, this time to the cotangent squared of x. So that's the other identity. So in here, unlike the other types that we have discussed, wherein when we split a particular function, we only take one function from it. Or if I may say, we subtract only one from its exponent and set aside that particular function which we took from the exponent. This time, we don't subtract one, but we subtract two. So you are to split the n, the exponent of the secant, and the cosecant into two exponents. One which is explicitly equal to 2, and the other one, of course, is n minus 2. That way, the function secant squared or cosecant squared, which you have set aside, which you have subtracted from the main function, will this time stand for the derivative of the function that will be using the identity that is written here. So for example, if you look at the example that is given here, you only have one. You have the secant of x raised to 4. So since you are to subtract 2 from the secant, automatically the secant squared which you took from in here will be the derivative of the function that is equivalent to the remaining function, which is secant squared of x. Why I'm saying it's the derivative of the function that is associated with the secant squared of x. It's because you are to convert the secant squared of x to 1 plus tangent squared. You have it here now. This is the conversion of your secant squared x, and you will multiply it with the secant squared of x dx. Why do we do that? It's because this tangent function has the derivative secant squared x dx. So if you will distribute, or if you will multiply the tangent squared of x plus 1 to the secant squared of x plus 1, it's readily integrable because this tangent squared of x that you have will be processed using power rule. So you have now tangent squared of x will be becoming tangent cube of x over 3. Your u in this case, the u here is the tangent. The n is 2. The du of the tangent is the secant squared of x dx. So that is why it became tangent cube of x divided by 3. As for the second squared of x dx, the integral of that is tangent of x. It's a simple trigonometric integral using only the formula for the integral of the second squared of x dx. Okay? So if this is cosecant, for example, this is not cosecant, you will process the cosecant in the same way that you have processed here the secant. Take a cosecant squared from the cosecant function, which is raised to an even positive exponent, and you set it aside together with the dx. The remaining cosecant function, which is raised to an even exponent, you convert to this identity, which is a function of the cotangent squared of x. That way, the cotangent squared of x that you have there, once multiplied to the cosecant squared which you have set aside, can be easily processed using power rule. Okay, so it's the same principle that we have in here with the second. Set aside a function that has an even positive exponent equal to 2 for the derivative of the identity of the remaining function. Okay, so that's our type 5. Now, before I go to the last type, which is, as I've said, the simply yes, because it will simply be following a formula. Do you have any questions? Yes, John. Arsenio.
Miss, if we are going to multiply tan squared to second
Uh-uh.
squared, Miss, wouldn't
Uh-uh.
the exponents be added?
No, if you're going to multiply tangent squared of x to secant squared of x dx, this secant squared of x will be your du. The tangent squared of x will be your u raised to n. So you will not add the exponent. So your tangent squared of x has the exponent 2. So when you evaluate it using power rule, that will make it 3. So tangent cube of x over 3. I am not sure if I understood well your question. So you don't add the exponents of these two because this one is tangent and this one is secant. This secant squared here is the one that you have converted to the tangent, which is associated to the secant squared x here, which is its derivative. Did I answer your question?
Yes, Miss. Thank
Okay.
you.
Sige. Any more question? Okay, I will clear first my screen before we go to type 6. It will follow the formula that you have in here. It's a combination of the sine and cosine class, but unlike type 2, if you can still recall type 2, it's a combination of sine and cosine. In type 2, your sine and cosine is raised to exponents m and n. In this case, class, your sine and cosine here, and your sine and your cosine together with another cosine are all having exponents equal to 1. Now, what makes it unique than type 2 or compared to type 2 is that the angles of the functions that are written here are not equal. So you cannot have them combined. So example, this might be sine of 2x and this is cosine of x. Or this is sine of 2x and this is sine of x. So the angles are not the same. Or cosine of 2x and cosine of x. So if this is the case, any of this combination here, as long as the sine and cosine has exponent equal to 1, you convert the expression that you have here into this particular identity or equivalent expression. So what do we do with the m and the n? We simply either add them, as you can see here, or subtract them. Okay? Now, if it's a sine and cosine combination, the one that you have here, you have 1/2 the sine of, you add the two angles of the sine and cosine for the first sine function. For the second sine function, which you will add to the first, you subtract. So it's m minus m. If it's both cosine with angles not the same, it's still 1/2. But this time, instead of having a sine function here, you will have a cosine function. So it's exactly the same as the formula for the combination of the sine and the cosine. The only difference here is that instead of the sine, you'll be using cosine. Now, what about if you have both functions as sine? You have here two sine functions, the angles are not equal. So you will have more or less an equivalent formula than you have here on top. The only difference is this. So there are two. Instead of positive 1/2 here, you have negative 1/2. And instead of a plus sign here separating the two cosine, you will have minus. Now, why I say this is the simplest? If you notice, class, your original integral contains two functions. You can say two functions because they don't have the same angles. Now, in here, you also have two functions, but they can now be integrated individually, or you process the integral per term using the simple integral of either the sine or the cosine. So it's simple because you need not think of an identity to convert it. You need not multiply. You simply have to make use of this and go back to the elementary trigonometric integral of the sine and cosine. Use it. Now, I think to illustrate it better, you have here the example. So we'll tackle first the first two. Now you have here the sine and cosine. So you just copy the equivalent identity here. So you have a 1/2. What you do with the first sine, you have the angles added. So 3x and 2x. For the second sine, you have to subtract the 2. So m minus n in that particular order. So by the way, this is how you assign m and n here. And the way you add, it doesn't matter, but the way you subtract really matters because it's really m minus n. It could not be n minus m. Okay? Especially with these two in here, with this particular formula in here. Now, I will have an example which will make you realize that even if we have a positive or negative angle in this case of cosine, we still have the same answer. So going back to the example, we just follow the formula here. You have a resulting integral of 1/2 sine of 5x and sine of x. So we know the integral of the sine, right? It's just the cosine. In the case of the sine of 5x here, you need to introduce 5 to dx or multiply dx to 5 because that's the derivative of the u of this sine function, and divide by 5 outside the integral. So as a result, you have 1/2 multiplied 2. So this is the answer for the first integral. 1/5 negative cosine of 5x. And for the integral of the sine, it's negative cosine plus c. Do you get it? It's very easy. Now, if it's both sine, you have this formula here. So negative 1/2. The cosine of m plus n, so 3x plus 2x minus the cosine of 3x minus 2x. So you have negative 1/2 times the integral of cosine 5x for the first term and negative cosine of x for the second term. Then just have this integrated. The integral of the cosine is the sine. You just need to multiply your integral in the case of this first term by 5 over 5. So you will have 1/2 times 1/5 for the first. So you will have 1/5 sine of 5x. And for this one, it's negative sine x. So your negative 1/2 is in here. I think you need not multiply by negative 1/2 or distribute the negative 1/2 to the two terms here because that will not simplify the entire thing. So placing it in here would be better than multiplying the two terms that you have here for the answer of the integral multiplied by it. Any questions? Okay. Now we go to the third example. You have both cosine. So you can see here, if it's both cosine, it's positive and it's plus here. So the same formula. You add the two angles and you subtract the two angles. So you have cosine 5x for the first and you have cosine x for the second. You'll have integrated. If you'll have it integrated, you will have 1/5 sine of 5x here and you have sine x for the integral of the second. Okay? Now, there's a note here that what about if you will have cosine of 3x and cosine of 2x interpreted in this manner? In this case, class, um, you have here, I will interchange this one. So, para maintindihan nyo. So, in here, you have, this is your m, and this is your n. Okay? In this case, I will change this. I'll make this 2, and I'll make this 3. Okay? So, your m this time is 2, and your n is 3. So, there's a typo error there. The manner of writing the two cosine function is very important. Even the manner of writing the two sine function, because the first argument of the two functions that you see is m. The second is n. So when you subtract, it really matters. So in here, let's look at what if it's written like this. So you have cosine of 2x plus 3x because we're adding. So it's still plus cosine of 2x minus 3x. So you have negative cosine of 5x plus cosine of negative x in this case. 2x minus 3x is negative x. Now what happens here? Why is it still written in the second part here as positive cosine of x? Now if you recall in your integral calculus, no, not integral calculus, but rather trigonometry in high school, when you measure an angle in counterclockwise manner, the sign of that angle is positive, right? If you measure the angle in clockwise manner, so this one is counterclockwise, this one is clockwise, the angle is negative. In the case of the cosine class, let's say I'll get this one, a cosine of 180 degrees, that's negative 1. In the case of the cosine here, it's cosine of negative 180 degrees because the manner of measuring is clockwise. So it's still negative 1. So in the case of the cosine angle class, the manner of subtracting or adding does not matter because whether you do it clockwise is 1 or counterclockwise, the cosine value is still the same. So that's the primary reason why your negative x here is still positive x. So if you interchange the writing of the cosine of the integral of a two cosine function with different angles, the answer will not be affected. For the first part, you still have 1/5 sine of 5x for the integral. And for the second part, you still have sine x. So it's the same as the one that you're seeing above. So the two, having the two angles interchange, will have the same answer because of this concept regarding the cosine of a positive and negative angle. Do you follow? Do you follow, class? No question. Okay, so if there aren't any questions, I will clear my markings again. And we'll go to the last. Okay, this time, look very closely. You don't have 1, but you have 3. 1, 2, 3. What will you do if you have that? Because in your identity, in the identity that was provided to you only have 2 functions here. What will you do? In this case, since we have the same angles here, you combine first the 2 angles in a manner that it's, shall I say, the sum of the angles will be the third one. So you don't combine 2 and 3 because that would be 5x and it cannot be combined here with the cosine of x. You cannot also combine 1 and 3x, cosine x and 3x rather, because that would be 4x and it cannot be combined with cosine of 2x. So in this case, what you will combine would be these 2. You combine these 2 first because when you add the angles, that would be similar to this one. So write as, so you could see here, cosine of x, cosine of 2x times cosine of 3x dx. And these two which you have placed in a parenthesis, you process using the identity that was shared to you on top. So the cosine of the two angles will constitute the, first you add the two cosine, or rather you add the two angles for the cosine, and you add to it the difference of the two angles. So x minus 2x or 2x minus x, it's still cosine of x. So this is it, as per our identity on top. So I'll go back to that so you will recall this is our identity here. Okay, 1/2 the cosine of the sum of the two angles plus the cosine of the difference of the two in the order m minus n. Okay, so let's go back here. And that's what we're doing. So this is the equivalent identity of the first. Looking at it intently, this is what I was saying a while ago, that this cosine of 3x here is now similar to this, right? So you can distribute this cosine of 3x as a multiplier to this and this. As a result, you will have cosine squared of 3x here, and you have cosine of x and cosine 3x here. Now, this cosine squared of 3x is under type 1. And this will be case 2. Type 1, case 2, wherein your cosine or your sine is raised to a positive even exponent. You will convert this cosine squared of 3x into its equivalent double angle equivalent. So you double the angle here, so that makes it 6x. So it's 1 plus cosine of 6x over 2. Okay? Whereas this one will be converted using this formula that you have used here on top. The cosine, the product of two cosines having different angles. So you add the two angles, that would be 4x. You subtract the two angles, that would be 2x. So this is it. Now both, this one by the way, will have over 2. So there's a typo error here, class. So you should have 1/2 here. But actually in here, the answer is already correct. So when you have this integral process, that's 1/2 x times 1/2, so that's 1/4. The cosine of 6x here, when you integrate it, needs that you multiply the integral by 6 over 6 because of the derivative of 6x, which is 6dx. So meaning you will have 1/6 multiplied to 1/4. The 1/2 and the 1/2. So that makes it 1 over 24, the sine of 6x. We come to this, you have already 1/2 times 1/2, that's 1/4. Times another 1/2 here, so that would be 1/8, sine of 2x. 1/2 times 1/4 for the cosine here of 4x will be 1/4 times 1/4. So that's 1 over 16, the sine of 4x. Plus C. So in here, in just one example, you made use of the identity of the product of two cosines with different angle twice. You did it here first, and you did it here second. Aside from that, this is an example which incorporates not just incorporates rather two transformation. One for this particular type 6, and the other one is type 1 case 2, wherein you're dealing with a cosine or a sine which is raised to a positive even exponent. You have any questions here? Any questions? None? So this covers everything about trigonometric transformation. Okay, in terms of trigonometric transformation, you have 6 types, all using identities to convert complicated trigonometric expressions to expressions which you can process using the previously learned technique of integration. So this is your type 1, sine and cosine. Type 2 is a combination of sine and cosine raised to exponents. Type 3 is the tangent and the cotangent. Type 4 is the tangent with the secant and the cotangent with the cosecant. Type 5 is just the secant or the cosecant standalone. And type 6 is the only type here wherein it's not raised to any exponent other than 1. The only difference is that the angles are not the same for the functions that are multiplied. Do you have other questions or concerns regarding this topic before we'll have a 5-minute breather, then we'll continue with the next topic? Do you have any question? Okay, there's none. So if you could see, class, our next topic here, if I will scroll down, is you have a lot of examples there to read. Our next topic would be integrals yielding inverse trigonometric functions. So integrals like this, rational, wherein the denominator is a square root. This one is rational, but the denominator constitutes the sum of the square of a real number and a function. And this one, which contains a radical and a variable. So these are the three new integration formulas that will yield the inverse trigonometric function. So you can see it has inverse sine, inverse tangent, or the arc sine rather. The arc sine, the arc tangent, and the arc secant. Okay? Now I'll give you a 5-minute breather to do your personal necessities. We'll go back. You need not leave Zoom. Just stay muted. We'll come back at 3:37. I'll stop sharing momentarily. Okay, so we're now on integrals yielding inverse trigonometric functions. So there are 6 formulas here. Actually, all in all, there are 9, but we'll just have the first 3. The other 3 can be determined using the first 3 that we have here. And the last 3, which makes it all 9, is related somehow to the first 3 that we have in here by means of only of a constant. Okay, so let's look at this one. So when we differentiate then in your differential calculus, the arc sine of u, this is your derivative. Du dx, you get the derivative of the argument of the arc sine, and you divide the answer to that by the square root of 1 minus that same argument, which is squared. For the arctan, the same, you take the derivative of the u, and then you divide the answer by 1 plus u squared. In the case of the arc secant of u, you also get the derivative of the u, and you divide it by u, square root of u squared minus 1. So these are your differentiation formulas then for these different inverse trigonometric functions. It follows then, class, that if you are to integrate these answers or these derivatives or this particular inverse trigonometric functions, it will yield the trigonometric functions that were written here on the left side. So integrating the answer of the derivative of the function gives you the function. Okay? Now, this will be how you're going to interpret it. You have to first and foremost identify the u. So this has to be 1 minus the square of the u. And then the du here, just like the du in here, should be interpreted as the derivative of the u, not the u squared, but the u of the function that appears under the radical sign here, in here, and in here, which does not have the radical sign. So as long as the derivative of the u is there present, then you can answer this particular inverse trigonometric functions if the denominator of these rational expressions are the way that they are written here. Now, recall. So you have learned in your trigonometry again, high school, that if you add the arc sine and the arc cosine, the answer is 90 degrees, or that's your pi over 2. The same thing with the arc tangent and the arc cotangent. And the same thing with the arcsecond and the arccosecond. This brings about the three sets aside from the three formulas that you have in here, which does not need a separate integration formula. If you know already the answer to the arc sine of u, then all you have to do is subtract it from the pi over 2. Then that would be your arc cosine. Okay, or shall we say pi over 2 minus the arc sine of u is equal to the arc cosine of u. So there's no need to have a separate integral that will yield the arc cosecant of u. The same thing in here for the arc cotangent of u. The arc cotangent of u is just pi over 2 minus the arc tangent of u. The arc cosecant of u is just pi over 2 minus the arc secant of u. So they differ only the sine or the arc sine and the arc cosine. The same thing with the arc tangent and the arc cotangent, rather cotangent, yes, and the arc secant and the arc cosecant. They differ only from each other by a constant. And what is that constant? That constant is pi over 2. So this is your second set of formula. So this is the first set and this is the second set. This is how you should relate the arc cosecant, the arc cotangent, and the arc cosecant of u to the three inverse trigonometric functions that you have in here. Now, what about the last three? So I said there should be 9, but actually they are just taken from the first three. So the last three is actually a modification of the expressions that you are seeing here on top. So I will show to you one derivation, the others you can read it on your own, but what is important is really the formula. So again, I will annotate now what is important is the formula. So you have 1 here, you have 2, you have 3. These are the 3 main formulas. This one is the 4th. This is where you're going to get the arc cosecant of u. This is the 5th. This is where you're going to get the arc cotangent of u. And this is the 6th, the arc cosecant of u. Now, what about the last 3? Okay, I will clear my marking so that I can go down. So the last 3 would be a modification, as I've said, of what you have in here. If you look very closely, class, to the 3 main integrals here, yielding the inverse trigonometric functions, the constants that are added or subtracted to or from the u squared is all 1. So you have 1, 1, 1. So what about this is not 1? What about this is any real number? Can't we not answer the same functions that we have in here? If let's say, for example, this is 9, this is 25, this is 4. Okay, so that question will be answered after I have shared to you the derivation. So what about in here for the arc sine of u, instead of having a 1, you have an a squared, a constant, which can be represented as a squared. And by the way, it need not be a perfect square like a 9, a 4, a 25. It could even be an 8. Anyway, you can place their square root of 8 squared. That would still be 8, the constant that you're seeing here. Okay? So now you don't have a 1, but you have an a. So let u equal to 80. Okay? In this case, your u is 80. Your du, of course, is ATT when you differentiate this one, left side and right side. From this particular expression that you have here, if u is equal to 80, then t is equal to u over a. So what we're going to do is we're going to place here a squared. The u you're going to change to 80, which you're going to square. And the du should be replaced, the du, the original du, should be replaced by ADT. Okay, I hope you can follow through again. I will enlarge. You let the u equal to 80, You differentiate this, that would be a dt, and you take an expression of the t from in here, and that would be u over a. So in here, it's u over a. The purpose here is that you will have an equivalent expression that you can integrate later on comparably or comparable to this one. It's just 1 minus u squared in the denominator. Okay, so now I'll copy the a, so it's still a squared. The u, which is 80, I'll place here. It's squared, so I will square. The du should be a dt, so I have it there. Now, you see this a squared and this a squared, it can be taken out. It can be factored out because anyway, it's a perfect square. So you place it before your radical sign and you are left with 1 minus b squared. So what happens now is that this a and this a will just simply cancel. So this is actually the arc sign of t, right? This one is the arc sign of t. Just like, I will first scroll up. Just like you have here the arc sign of u. Now the u will change to t in here, in terms of t, at. So this is the arc sign of t. But what is t in the first place? Isn't it t u over a? T is u over a, so you place here u over a. So whenever you're given an integral wherein it's not 1, this one is not 1, but any real number, what you do is you still have the answer, the arc sign of u, but you divide it by the value of the a here. So if this is 9, this should be 3. Okay? What is important is that whenever you have this expression here, the u here, the u only, should have its du here intact. So the expression 1 over the square root of a squared minus u squared should be multiplied to the derivative of the u only in here. Okay? This a can be any real number. Any real number. Anyway, you're just going to place it there. So instead of only answering the arc sign of u, this time you will have it the arc sign of u over a. The same principle is followed when we deal with other functions. So in the case of the arctan, if it's just 1 here, 1 plus u squared, you only have the arctan of u. And since you already have this real number, there would be changes. Your formula now will be 1 over a, the arctan of u over a. So this is your added formula for the arc sign, wherein your u squared in the denominator is subtracted from a real number. So this is your 7 formula. And this is your 8 formula for the arctan, wherein the a squared here is not equal to 1. So you have 1 over a. Now, what's the difference of that from the one that we have here originally? It's the 1 over a here and the over a in the u. Okay, so that's our 7th and 8th. Okay, this is our 7th formula and this is our 8th formula. If we have a modification for the first two, we also have a modification for the last. So this is it. So the last one, you have 1 over the square root of u squared minus a squared. In our original formula, it's u squared minus 1. Okay? And this one indicates that your u, we are concerned only with the absolute value of the u. Okay? The absolute value of the u. So if that is the case, if your original formula has second of u only or the arc second of u only, whenever this one is a real number, you will have this last formula here. You have, just like the tangent, 1 over a, the arc second of u over a plus c. The derivation is exactly the same as the first one, wherein you change the u to at. And that follows. The rest of the derivation is up to you to follow through. Here, anyway, it's written. So this is your 9th This is your ninth formula for the integral yielding the inverse trigonometric function. Do you get it? Any questions before I go to examples? Okay, so no questions. We'll go down to the examples. We'll go down to the examples that we have. Okay. We have here a case of this is a squared minus u squared, which is an arc sine. Your u is x, your a is 3, the du is dx. So we're okay. So the arc sine formula, x over 3, or the arc sine of u over a. Let's see. What about the second one? The second one. So you have a here as 3 and u is 2x. It follows that this should be completed by multiplying it with 2, and we'll place here 1/2 before our integral. So you'll have 1/2. You have here 1/2. The arc sine of the u, which is 2x divided by 3. Very simple. As long as you can identify right away that this form is yielding an arc sine. Do you get it? Okay. No question? Clear my markings. What about this one? So you'll have here an a, which is 3, is still radical, and your u is x minus 1. Your du is still dx. So same thing, it's still an arc sine of u. So your u now is not just x, but x minus 1 over 3. Okay? Now, we'll go further down. We'll have this one. Here, a is 2, u is sine of x, the du is cosine of x dx. So this is your du. So still arc sine. The arc sine, take note of what u, sine over a, which is 2. The arc sine of sine x over 2. Do you follow? Okay, still another arc sine here for the fifth example. Go up. So your a, here is the example wherein a is not a perfect square. Or rather, a squared is not a perfect square. So your a is square root of 5. Your u is e raised to x because this one is already squared. The du is e raised to x dx. This is your du. So the arc sine of u, which is e raised to x, over a, which is square root of 5. It need not be a perfect square. So in that case, you have already square root of 5. That's for the integrals yielding the arc sine. Now, what about if it's not anymore having a denominator which is a radical sign? So this time your denominator is the sum of 2 squares. Your a is 5, or the square root of 25. Your u is x cubed, the square root of x cubed. And the du is 3x squared dx. Derivative of the x cubed is 3x squared dx. What do you lack here is the 3, and you place 1/3 here. And this entire thing is your du. So the formula of the arctan is 1 over a. So you have here 1/5. The arctan of the u, which is x cubed over a, which is 5. The 1/3 that is being multiplied to this answer came from the 1/3 here. That completes the 3, which makes it 1, that is needed for the derivative of your u. So 1 over a, so you can see here 1 over a, 1 over 5, the arctangent of u, which is x cubed over a, which is 5, plus c. Question? Nan? Okay, I'll clear my markings. And then we'll have the 7th. Whenever class you see a square root, wherein we have the u squared written first minus the constant, then that's the arc second. This one here, the u squared expression is written first and then followed by a number. So your u there, this case is, what's the square root of that? 2x, right? Your du is 2 dx. Your a, square root of 36, is 6. Now, your du needs a 2. You only have dx here. So I'll place here 2, I'll place 1/2 before my integral. Now remember that if this is u squared minus a squared, this has to be u. So the u that I need here is only 2x. So the other 2 here I'll place outside. So that makes it 1/4. See that? Because I only need 2x here. I only need 2. So the other 2 will be placed outside. So that makes it 1/4. 1/4 times the answer of the arc second. So it's 1 over a, which is 1 over 6. The arc second of u, which is 2x over a, which is 6. So 1 over 24 arc second of, so this could be simplified further by taking out the common factor, which is 2x over 3. That's for the arc second. Do you follow? Yeah. Okay. We'll clear my markings here. And we'll proceed with the last. Okay. What about this? This may look like a u squared minus an a squared. So let's get this rolling. If your u squared is 2x, so your u is e raised to x. The du, the derivative of e raised to x, is e raised to x dx. Right? Now, your a, if a squared is 16, is 4. So it follows that your derivative here lacks the e raised to x. So I'll place here the e raised to x. We can only have an arc second here if the form of the integral is du over u square root of u squared minus 1. So hallelujah. Why I'm saying hallelujah? Because I cannot introduce here e raised to x without writing here e raised to x. Just timely because I need to place here e raised to x because there should be a u before the square root of u squared minus 1. So introducing e raised to x over e raised to x does not alter my original integral because it's just 1. But it makes it even more the arcsine function. It will yield the arc, no, not arcsine, the arcsecond function. So what is it? So it's 1 over a. So a is 4. So 1 over a, the arcsecond of u, which is e raised to x over a, plus c. See? So you just have to do things here step by step. What is important is you know the form of the integral that yields the inverse trigonometric function. The form followed by the formula. It's very important. You have any questions here? Is everything clear? I close all my markings. You don't have any questions? Sige. We'll have another 5-minute break. My time is 4:02. You have another 5-minute break. You may have your other things there. You want to go to the bathroom or drink water. Come back at 4:05. Okay, for now, I will just pause the recording. Okay. So we are now on integration by parts. You integrate a given expression by parts, just like the way it's named, by parts. So when do we use integration by parts? So number one, we use integration by parts if you're dealing with a polynomial. So what do we mean by a polynomial? It's an x, it's an x squared plus 1, it's an x minus 1, it's a 2x minus 2, or something like that. That's a polynomial. And another function. So the other function could be cosine, could be sine, could be tangent, could be even ln, it could be even exponential. So when your integral deals already with a combination of a polynomial and any of those transcendental functions that I have mentioned, so your trigonometric function is a transcendental function. Same thing with the logarithmic function, the exponential function. Even in the inverses of your trigonometric function, you have to use integration by parts. Now, when you use integration by parts class, it is always suggested that you assign your polynomial as the u. The remaining expression will be the dv. So, what do you mean, Miss Ali? When you're given an integral, which is a combination of a polynomial or any of the transcendental functions that I have mentioned, you have this form, the udv form. You assign the u to the polynomial and you assign the dv to the remaining function, meaning the rest after you have already taken out the polynomial. Okay? Now, what's the purpose of first identifying what should be your u and what should be your dv in this case of this integral, which will be processed using integration by parts? When you process an integral using by parts method, this is your formula. This is the only technique of integration which has two terms in its formula to follow. That way you come up with the answer of the given integral. The usual way of me teaching this to my student is this, okay? I will first clear my markings. Example, I give you a very, very simple example. Let's say, for example, you have the x. It's in here already, the x and the cosine of x. So I will just clear my markings here and present what I have in here below. Okay? Okay. I'll use this one as an example. Then I write the explanation here. Your u is the x because it's the polynomial. The remaining expression, the sine x dx, is your dv. That's your dv. This entire thing is your dv. Okay? This is like writing it as u dv. in that particular order. Your x is the u, and the sine of x, dx, is the dv. Since the integration by parts will follow the formula uv minus the integral of v du, that's the formula for integration by parts. This is how you're going to do it. That way, you will not get confused on how will you process the given integral. I usually write my u here on the upper left side. So if I'll divide my paper into 4 sections, so this is my u. So what's my u? That's my x. Beside it, I'll write the du. The du, the derivative of the u, is the dx. Now, since we already have represented the sine x dx as the dv because that's the remaining expression after you take out the x, I'll write it here. The dv is sine of x dx. How do you find the v? Because it appears here in the formula. You integrate this part. Okay? If you integrate the left side, that should give you the v. If you integrate the right side, of course, integrate it based on the formula that is applicable to it. So the integral of the sine x is the negative of the cosine of x. Right? The integral of the sine x is negative cosine of x. Then what do you do? I usually tell my students you do this pattern. Based on the formula, you cross uv, meaning the answer to this, the integral of x sine x dx is equal to uv. I'll multiply this 2, so that would be negative x cosine of x minus the integral of, this is what this one, the v du. So cross, and you have this v du. Go down, vertical. The v and the du should be multiplied. So negative cosine of x dx. So your answer here would be negative x cosine of x. This is negative and this is negative. That would make it positive. The integral of the cosine is sine. So plus sine of x plus c. So this is our answer here on top. So the pattern always is u dv. Here on the first column, then you answer on the second column the du for your u and the v for your dv. Then the pattern of processing is it like this. Okay? Slanting and then vertical down on the second column. Why would you do that? Because the formula for by parts is uv minus the integral of v du. That's how I teach my students. But if you're not comfortable of doing like this, wherein you write your u here and your dv here, differentiate your u, you place it here, and integrate your dv to get the v, it's fine with me. But as long as you know that the formula for by parts is uv minus the integral of v. Okay? Now, we have here examples. So we'll do the examples here the way I used to do it. Okay? If you're not fine with that, if you'd like to identify other things, other method that you're comfortable with, then it's fine with me as long as you understand what you are doing. This is the integral of ln x dx. There's no polynomial here, class, right? So since there is no polynomial here, what you're going to assign as your u is the function itself. Okay? What you're going to assign as the u is the function itself. So if I will make, again, I will have my u as the ln of x, and my dv, of course, is the dx. Okay? And by the way, class, what tells you, what is the very important thing that you should remember when you choose your dv? When you choose your dv? When you choose your dv in the original integral expression in the form of u dv, first and foremost, that dv should be integrable. What do I mean with integrable? In our language, dapat may integrate siya. You don't choose a dv expression here in the original integral which you cannot integrate or will even make things complicated for you. It is always suggested that your dv will be an expression which is easily integrable or will make the process of integration simpler, not complicated. Okay? So in this case, we choose dx as the dv because if you integrate this, you integrate the dv to give you a v, the answer is simply x. If you differentiate your u, the answer would be derivative of an ln x is dx over x. We know that the derivative of ln u is du over u. So this is the derivative. Now then we follow the crisscross process. So you have minus or the integral of ln x dx is equal to uv. So you could see it here. It's x ln of x minus the integral of v du. So you have x times dx over x. This cancels. This is integrable. That gives you x minus. This one is x ln x. So you see? If you do it like this, it's easier to follow rather than having one line here. But it all still depends on you. Before I proceed with the third example, do you have any question? Okay. I'll clear my markings here. Now we go to number 3. Remember what I said to you a while ago? You choose a u that is complicated. Okay? You choose a u that is complicated and the rest of the expression which is readily integrable as the dv. So in this case, you assign the u as ln of x squared. Now class, you don't assign the u as the polynomial here as suggested when you have an x times, let's say, a trigonometric function, because the ln of x squared here, if you will assign this as your dv, cannot be integrated. So you don't make this as your dv because it cannot be integrated. Okay? Now, so what do we do? So you'll have again you construct again your, this one. Your u is the ln of x squared. Now, the dv, of course, initially will be x dx. The remaining expression after you took the ln of x squared. Now, what's the derivative of the ln of x squared? Du, which is 2x, over u. Right? Du is 2x dx over the u, which is, sorry, your u is x squared. Okay? 2x dx for the derivative of u, which is x squared, and over u, which is x squared. What about this one? It's this. When you integrate that, the v is equal to x squared over 2. If you integrate this, that's x squared over 2. Then just process. So you will just have to process this one. Use a different color. So cross, have that. So your answer will be, for that integral will be x squared over 2 ln of x squared minus the integral of v du. This one, the v and the du. So integral of x squared over 2 times 2x dx over x squared. So I place here x squared over 2 ln of x squared. These 2 cancels. This x squared cancels, giving you an integral to process as x. So that would be minus x squared over 2 plus c. So this one has a typo error. This should be divided by 2. Do you get it? You choose the complicated function or expression as the u always. Choose the dv as the expression which you can readily integrate. You don't choose a dv which you cannot integrate. For example, if you choose dv here as ln of x squared dx, it cannot be integrated. So don't do that. So you have to assign the u to ln of x squared. You will know a lot of things about by parts as you practice solving. So not everything could be taught in one setting. So as you practice solving, you get to know how it's to be done. Or if you're dealing with this particular function paired with another function, it's better that this function is the u and the other function is the dv. Okay? But generally, that's how I suggest it. The complicated expression should be the u, the dv should be readily integrable. You have any questions? No questions? Okay. Then we'll proceed to the fourth example. You still assign u and a dv. So we'll divide this into 4 portions again. Now, in this case, class, you can assign the polynomial, the x, as your u, and the exponential function as your dv because it's readily integrable. So your u is x, your du is dx, your dv is e raised to x dx, and your v is e raised to x. Then what's the answer? Cross and drop. Cross and drop. Cross. So that would be your x e raised to x here. Drop. The integral of e raised to x dx is e raised to x. Okay, plus c. Cross and drop. Question? Okay. We're here again. We'll go down. We'll draw another table. So in here you have now you have cosine of 2x, only 1 dx less. Cosine of 2x dx multiplied to x squared. So cosine 2x is readily integrable. So the polynomial should be your u, just like the x and sine x here. So u is x squared. Du is 2x dx. dv is cosine of 2x dx. b is 1/2 sine of 2x. The integral of the cosine is the sine. We need to place 1/2 because of this 2 in here. Okay? And then what do we do? Cross and drop. Cross and drop. So you have 1/2 x squared sine of 2x. You see it here. And then 2x multiplied to 1/2 sine of 2x will cancel the u. We cancel the 2. So that will give you an integral. So your integral here, I'll write first the answer, huh? So you have 1/2 x squared sine of 2x minus the integral of, you have 1/2 sine of 2x times 2x dx. Okay, you see this? Now we cancel the 2's. So I'll have 1/2 x squared sine of 2x. And you have here minus the integral of x sine of 2x dx. You say, Miss, wala pa man matapos. Precisely because whenever your polynomial is of degree higher than 1 and it's multiplied to any of your transcendental function, trigonometric function, exponential function, it will dictate how many times you do by parts. What will dictate how many times you do by parts? The degree of your polynomial. So since this is second degree, you will do by parts twice. If this is cube, you will do by parts thrice. It's easy if it's just a first degree polynomial. But higher degree polynomials requires you to integrate by parts, the number of times of which will be equal to the exponent or the degree of your given polynomial. So you will use another by parts for this one here. So we will do that. This is where we're going to end. We'll do that. So you have another u in this case. So your u here is x. Your du is dx. Your dv is sine of 2x dx. Your v is negative 1/2 cosine of 2x. What then should be the answer? Another cross and drop. So cross and drop. The answer to this should be added to the first one. So I'll write it in here, huh? So you will have 1/2 x squared sine of 2x. This one, it's minus, right? So minus 1/2 x cosine of 2x minus the integral of v du, that makes it plus the integral of v du, which is 1/2 cosine of 2x dx. Because the answer of this is another uv minus v du, the minus in the second term, negative of that makes it positive. So you just have to process the integral of this. So let's see. So in here, you already have the 1/2 x squared sine of 2x. And you have minus 1/2 x cosine of 2x. So this is minus. It should be minus. If there's a typo there, that should be minus 1/2 x cosine of 2x, and this one should be a plus, because negative, that would make it positive. So this should be plus. You already have 1/2 here, but you needed another 2 for the dx here, for the derivative of this 2x. So that would be 1/4 now, plus 1/4 sine of 2x plus c. So you have done integration by parts twice. Why is that? Because of the degree of your polynomial here, which is second degree. Okay, do you have any questions, class? So the first integration by parts you did was on the original x squared cosine of 2x dx. This is the first one we did. So we have minus 1/2 sine of 2x here times 2x dx, which yields another integral which needs to be processed using by parts because of the x sine of 2x here. This is processed again using another by parts, so this is the other by parts. So it yields now 3 terms. Any questions? Yeah, are you sure there aren't any questions? Okay, I will clear my markings. And stop sharing.